Okay, so last time we saw that a curve in R3, if you translate or rotate, its curvature and torsion are unchanged. So some kind of a similar thing we have seen in the plane curves. The plane curve, if you translate or rotate, its curvature is unchanged. And also we have seen kind of inverse, converse to that. Namely, if the curvature is given, then you can get back the curve. Of course, but there is, as we have seen earlier, we don't get one curve, we may get a lot of curves, because if you give me one curve, any translation also will have the same curvature, any rotation also will have the same curvature. So up to that, there is only one curve. So that's what we have seen in the case of plane curves. So something similar to that we want to look at about space curves, curves in R3. Curvature alone will not work. There are simple examples. I mean, you can check. Namely, suppose you take the curve gamma t is equal to, this is in cos t sin t 0. So this is a circle of radius 1 with origin as the center in the plane, in the xy plane. You can take another curve gamma bar t cos t sin t, something like t. So this is the helix. Now in the circular helix, so if you look at its look at the gamma dot, which is minus sin t cosine t 0, and gamma double dot t, that's going to be minus sin t minus cos t minus sin t t. So curvature is the norm of that, namely 1. Curvature is going to be 1. What about here? You take the tangent vector derivative, you get minus sin t cosine t 1. Let's take the second derivative, you get minus cos t minus sin t 0. The norm is 1. So this will also have the same curvature as that. Whereas this curve is a plane circle, whereas this one is a helix, goes spring-like. This curve. So curvature will not give you, and one cannot translate or circle. If you translate, you are going to get only circle. Even if you rotate in whichever way you like, you are going to get only a circle. You will not get a helix like that. So therefore, curvature will not determine the curve. This curve can never be obtained from here by taking translation or rotations any number of times. So therefore, curvature is not enough. So next question is, if torsion also is given, because both of them have same curvature and one cannot be obtained from the other using any kind of methods. In fact, more generally, if you know about topology, that one is compact, this is not even compact. So there is no way you can, and this is bijective parameterization. This is just periodic parameterization. So there's quite different. No way you will be able to get one from the other, even. Okay. So therefore, will torsion make it? Torsion of this you can compute is going to be certainly different from 0. This is not going to be 0. So therefore, they are not going to come from the same. If you could translate and get or rotate and get this, then they should have the same torsion also, but this will not have torsion 1. One can compute, it's quite simple, one can compute and find out the torsion. So I'm not going to compute it. So therefore, the question is if torsion also is given. So plane curves can be completely determined up to translations and rotations by the knowledge of the curvature. And space curves you cannot. So for space curves, the next question is, if the torsion is given, can you think? We had discussion about it, that if you translate or rotate, rotation has been defined in a very in a particular way. We call them rigid motions. If you translate or rotate, the curvature as well as the torsion are unchanged. They are going to be the same functions you get. It doesn't change. So there is a natural question, like what we did in plane curve. If the curvature and torsion also is given, can you get the curve? Well, again there is a problem, because if you give me one curve, if you translate, the curvature and torsion are going to be same. If you rotate, again the curvature and torsion are going to be same. So therefore, you don't expect to get back the curve. But get back a curve, from there I can translate and rotate. These are things which cannot be avoided. They are unchanged. They will not change curvature and torsion. So knowledge of curvature and torsion, you will have a lot of curves. Given one curve, I can get plenty of them. Question is, are there any other? And the answer is no. Any two curves, if they have the same curvature and torsion, then I can get one from the other by translating and rotating. So this is one part. Another part is, given curvature and torsion, what is the guarantee that there is a curve having that function, given function as the curvature and that as the torsion. So these are two parts. One calls it existence and unique, but unique not in the standard unique sense. Unique up to translation. That means you allow translate or you allow rotation. Then you get everything. From one of them you can get everything else. So that's the part that we are going to look at. So first let me talk about the existence part. If you imagine a space curve as a metal wire, solid metal wire, rigid metal wire, that means you cannot bend it anymore. So whatever is already bent, along the curve, you take it, you translate it upward, downward, whichever way you want. The curvature and torsion is unchanged. Similarly, you can rotate them. In whichever way you want, you can rotate them wherever you want. Then also, the torsion and curvature are unchanged. And what we are saying is that two curves have the same curvature and torsion. One can obtain from one by moving and rotating. That's it. So existence is a bit tricky because it is slightly beyond our scope, but let me just quickly tell you what it is. It's in the case of existence of curve with a given curvature in the plane curve, we just took the curvature, just integrated, and we have got it. Something similar to that we are doing, but only thing is that no simple integration works, because curvature and when it comes to torsion, curvature can be easily related because it's a second derivatives. Though we take norm also, that's a bit involved. Whereas in the plane curve we only took the signed curvature, so it was easier. But here it's a bit involved, but that's not enough. You have to also put torsion into it. So what is important is, so suppose let us say, by the way, this is the curvature given. So that's, and you also take the torsion. So they have to be functions from wherever the curve is expected to be defined, and these are all real valued functions. And remember one thing, if you want to talk about torsion, you need the curvature should be never vanishing. So it should always be non-zero. See, a continuous function, this is smooth. Both these are smooth, we have seen. They are assumed to be smooth. Then only you can discuss calculus. So, if it cannot be zero anywhere on this interval. Therefore, it should be either always positive or always negative. Because if it takes value positive at some point, the value negative at some other point, then in between it should take the value 0 by simple continuity intermediate value theorem. So therefore, either k has to be always positive or always negative. I mean, it makes no difference. One could ask one of them. One could assume the other part is very symmetric arguments. So let us take these to be smooth. Such that torsion we don't have much of an issue. It can be anything. It could be 0 and sometimes 0. Through some plane it has gone, then it must have deviated. This or that. Ks is positive for every s. Okay, so either case is always positive or always negative. So let's take Ks is positive. So now we are going to say how we get gamma. So to get gamma from alpha beta to the interval alpha beta to R3 such that it's such that its curvature is K and its torsion is going to be T. This is our question. Does there exist even one curve? If I get one curve, then by translation and rotation you can get infinitely many, and I am saying they are the only ones you can get. That's the second part. How many is the second part? Or how do we get others is the second part. But first part, do we get one? Okay. So what do we do is, because of torsion, straightforward integration doesn't work, even curvature. This could probably be still thought of, but we don't, we cannot integrate and get it. Torsion also. So the standard trick is the relations that we want gamma with what is that? Curvature and torsion is the Serre formula. So let's take so for the Serre formula, what is required is the curvature, the tangent, normal, binormal. Okay. So let us take three such functions: T, N, and B. These are all supposed to be defined on. So to find, this is basically what we have. We don't know whether there is one such. If we can do, then we are done. Do we have it? Then we are done. Interestingly, to get gamma, you only need T. Once you have T, you integrate, you get gamma. But then you cannot just take one relation and manage it, because torsion has to be, it will not work if you do like that, because you won't be able to get any curve, any fixed curve. So therefore, we have to find a relation between them. So to find this function smooth, R3, at every point, so every T you have T, or every point S you have TS, NS, BS. This is going to be TS, NS and BS. This is orthonormal. That's one of the conditions for every S. And follow right hand, what is that term? Rule. Okay? Right hand thumb rule or whatever. Okay? Is a right-handed system. And that system, I'm just calling it, that means this is, what is that? T cross N is equal to B, must be equal to B at every point. That is, if you want, I can write that. TS cross NS is equal to BS. system, right-handed, we should not forget to write orthonormal. That means the norms are 1 and they are orthogonal to each other. System for all S. For all S. Okay. It's not over. Now, well, that forms a right-handed orthonormal system at every point. That's what we know. But it also satisfies more conditions, these functions. That's where curvature and torsion comes into picture. And then we have to look at what to do with it. So what is the first one? The first one is d by ds of t at any point s is equal to ks ns. By the way, k is a real valued function, m is, these are all vector valued functions. Okay, so at every point we must have written as d dot is equal to kn. I'm just writing it in you. Similarly, second is d by ds of n at s is equal to minus ks ts plus torsion times binomial. And finally, d by ds of b at s is equal to minus torsion times ns. So this is the, but if you carefully check, what does it mean? These are all vector value. But if you look at the coordinates, then this could be written as, if you write t is equal to t1, t2, t3, the coordinate functions, then this will give you, these are real valued functions, t1, t2, t3, the coordinates, defined on again alpha, beta. And so for one variable calculus, from r, alpha, beta to r, t1, t2, 3 function satisfying this condition, and this will be n1, n2, n3. So if you write one of them at least, first one, so this will give you, you can similarly write all those. T1 at s is equal to ks n1s. That's the first coordinate here. Similarly, you can write T2, you can also write n2, I is equal to. So there are 3 equations here. 3 differential equations. Ordinary, simple, linear, everything. Quite fine. So there are 3 of them here. Similarly here, it will be d by ds of n1s at s is equal to minus ks t1s plus ts b1s. And again, put I. So there are 3 equations here, 3 equations here. So there are 9 differential, system of 9 equations, and there are 9 functions, namely t1, t2, t3, d1, d2, d3, n1, n2, n3. And you have to solve it. It's very important to see that these Hermitian property is very useful. So this is a matter of differential equations, solving differential equations. I leave it to you, refer some books where it's proved that this system has a solution. So that's this system. So if you write this system, the system star admits solution. Satisfying these conditions, satisfying the condition that this is orthonormal system, satisfying orthonormality condition. Remember, uniqueness is right now not even discussed. We don't look at that. With some extra conditions, this may probably be unique because tangents can be fixed with the initial conditions. And then, once you have your tangent, so So your gamma is going to be integral T1, integral T2, integral T3. So that solves, you can fix some point S0, S0 to gamma S is equal to S0 to S T1 U du, S0 to S T2 U du, S0 to S T3 U du, that gives you a gamma. So gamma dot is going to be T1, T2, T3, then T, and then the rest of them, because it satisfies this condition, you can immediately get the rest. So that is the general principle. So existence is more of existence of solutions of differential equations. Okay, so now let's look at the question of how many of them are there. As I was telling you, suppose you have one space curve, then if you make translations and rotations, the curvature is unchanged. Now suppose you are given two curves with the same curvature and torsion. Can you say that one can be obtained by translation and rotation of the first one, I mean the other one? That is the question we are asking. And the answer is yes. So it's an interesting proposition. So let us start with two curves. Let gamma 1, gamma 2 be curves. In R3, even in the earlier one, I did not take the curve, so it is nothing to worry. But now I have to be careful. Take only unit speed. Okay, the unit speed curves okay with curvature K and T from alpha to beta, of course with smooth curvature with the, no, I have to be careful. K with curvature K, that's all. K from alpha beta to R plus, no, it will not be 0, and T and torsion T from alpha beta to R with the same curvature and the same torsion. So this is what we take. Now, first thing is, see, to do calculus, especially linear maps, we will bring it to origin. So that's the first thing we do. So how do we do? Suppose one curve is like this, the other one is like this. Both have the same. So it's of course it's an R2. I'm drawing in the plane, but it would be R3 something. So what we do is we bring them to some point. In R3 you have this. So we bring it to here. So you have your alpha beta here, and so you will have some parameterization, namely gamma 1 here, and this is gamma 2. So what I want is to bring this here. So let us fix a point here. Let's fix a point somewhere here, interval. So we call it S0. And S0 will have an image here. So gamma 1, S0. And here, somewhat at the similar kind of place, and gamma 2, S0. So that's the. So let us bring it here. So what do? We will push this here, so it will come to the origin like this. This will come like this. So, well, another one will come. So what is that? What is that going to be? It's very simple. Let us take gamma 1 tilde s is equal to translated. So this is brought here. So gamma 1 s minus gamma 1 s naught. S naught is a fixed vector. Gamma 1 s naught is a fixed vector. So we are subtracting. Similarly, this guy. Gamma 2 tilde s is equal to gamma 2 s minus gamma 2 s naught. So one can easily check now. So this is a new, these are two new curves as I have drawn here. So here, this is your, which one is, this is your gamma 1 tilde. This is your gamma 2 tilde. It is just the same curve has been brought here. The picture is not all that good. So this has been brought here. This has been just shifted. Actually, it should be parallel. The way I have drawn it doesn't look. It's parallelly shifted here. That's how you get it. Okay, because just a translation. It will be, in some sense, they are parallel. Okay, so let us check. So what will happen to this? Gamma 1 tilde at s naught. Check. Gamma 1 s naught minus gamma 1 s naught, that is 0. Similarly, gamma 2 tilde at s naught is equal to gamma 2 s naught minus, this is fixed. Here there is no s, so it's already, so that's also 0. That's what I said. It is brought to the origin in the R. So now we work with these two. But how do you get this? Add gamma 1 s naught, you get this. From gamma 2 tilde, you get gamma 2 by just adding gamma 2. So it's for translations. And we are willing to accept translations. Okay? So from here to here, I mean, we don't know, but from here to this and here to this, we have a translation that is done. So now, still there is problem. So what we do, now we are going to say that we can rotate it and make it identical. And that requires some work. So to do that, so let us look at these two curves. Since, so let's fix that. Let, for these two, let T1, N1, B1 and T2, N2, B2. I have a caution I want to tell you. When we were discussing existence, we wrote coordinate functions by T1, T2, T3. But here it is not that. For gamma 1, you have tangent, normal, binormal, triple. For gamma 2, you have tangent, normal, binormal, triple. So I am writing this for corresponding to gamma 1 and gamma 2. So I am writing it B, the tangent, normal, binormal, triples of associated with gamma 1 and gamma 2 respectively. See, remember, gamma 1 tilde and gamma 2 tilde are obtained by translations of gamma 1 and gamma 2. But translations do not change the tangent, normal, binormal, triple. In fact, the derivative itself is going to be same, so there is nothing more. Beyond that, everything is same. So therefore, the tangent, normal, binormal, triple of gamma 1 is the same as the tangent, normal, binormal, triple of gamma 1 delta, which is the same as this. Similarly, we can write, and hence of gamma 1 tilde and gamma 1 tilde 2 tilde gamma 2 tilde respectively, because they are just translates and Tangent normal, binormal, ripple is unchanged by translation. So we are, this is, of course, if you look at this tangent normal, binormal, tangent itself, you can at least easily see it's going to be in the same direction because of the translation. Of course, physically I drew this, but it's very easy to check. What is the derivative of gamma 1 dot? It is gamma dot. So this guy is just derivative. This is a fixed vector, derivative is 0. So similarly, gamma 2 dot is that. Gamma 2 tilde dot is gamma 2. That is verified. Now the problem is for this curve, namely this is your gamma 1 tilde, this is your gamma 2 tilde. For these two curves at this point, you look at the tangent normal, binormal. Okay? So consider, let us write this, let us just write that. So that is at the point S0, T1 S0, N1 S0, B1 S0. This is a right-handed orthonormal system. And T2 S0, N2 S0, B2 S0 are right-handed systems. Okay, before getting into linear maps that we want, I want to make a little bit of understanding of what is this rotation that they're looking for. So before that, if you have you're familiar with your linear algebra, or else I will just make a small explanation. Suppose you have a vector, you have three vectors. This is very interesting for you to understand. Namely, suppose you have three vectors A1, A, B, C. Or A with of course coordinates A1, A2, A3. So you can write A1, A2, A3 and B1, B2, B3. These are three vectors you can assume, or you can even write down. If you take this matrix, suppose you evaluated E1, the standard 1, 0, 0, evaluated E1, then you are going to get A1, A2, A3. If you evaluated E2, this is 1, 0, 0. If you evaluated E2 in the 0, 1, 0, you get B. So this is A. And if you evaluated E3, you get. So that means this matrix is a very general thing. If you evaluated E1, you get the first column. If you evaluated E2, you get the second column. You evaluated E3, you get the third column. This is interesting because to understand what is happening. So let's look at let's come back to our, this you can generally work out. Let's look at what we have done just now. So let us take those three vectors, namely T1, T1, N1, B1. Just for fun. This is a matrix. So T11, T12, T13, N11, N12, N13, B11, B12, B13. So this maps the triple E1, E2, E3. This matrix, you can write it as a matrix, whatever way you like. I did not write the coordinates. You can write the coordinates at T11, T12, T13, N11, N12, N13, B11, B12, B13. This maps E1, E2, E3 to the vectors T1, N1, B1. This is a right-handed system. And this is a right-handed system. And by the way, of course, I don't need it, okay, so don't worry, you can even look at the determinant is nothing but the box product. You must have seen that. What is the determinant of this? Determinant of this is A1 dot N1 cross B1. This is the standard formula. You must have done this. That's the determinant. Which is easily you can determine that this is going to be 1. Determinant formula you can easily see because this cross product is actually equal to T1, so norm of that is going to be 1. That the square is dot product will give you norm square, that's going to be 1. So that's so this map. So what we are going to say is you look at the inverse of this. That will take E1, E2, E3. Similarly T2. Similarly you can now write T2 and I maps this to Ti and I Bi or I is equal to 1 comma 2. So what I want is a rotation from, and what is important is this matrix, the rows are orthonormal. Because T1, T2, T1, T1 and 1 B1 is orthonormal, T2, B2 and 2 is orthonormal. Therefore this is a not only orthogonal matrix, this is also having determinant positive, so this is a rotation. This is a rotation, therefore its inverses are also rotations. That's exactly the rotation that I am talking about. So what you do, from T1 you have a map to this, or T2 you have a map, whichever that you like. So you will have, first apply T1, okay, then first apply T1, N1, B1. This matrix you first start from here, then goes here. So this will be thus. Okay? So yeah. So let us take this map E1, E2, etc. E3 to E1, E2, etc. E3, and then so I will do T1 and N1 thus, and what we want is T1 N1 B1 should go to T2 N2 B2. Okay, so first from here, so you bring this backward. So this will bring T1 N1 B1 to E1 E2 E3, and then apply T2 N2 B2. I mean, I could have just written this. So these are matrices. I have not written the coordinates. Then it will become 3 by 3 matrices. They are rotations. So this is a rotation, this is a rotation, this composition is a rotation that maps T1 N1 B1 to T2 N2 B2. So this is the kind of thing that I am talking. I could have just written, but linear algebra is beautiful, one should learn, one should know this. So this is a rotation that maps, I am not talking about the general one, at the point S0, okay? That maps T1, these are all fixed at S0, though I have not. General thing you need not worry. So these are all going to 0, so you know at that point we are mapping the gamma at these points already they are all 0. Mapping T1 S0 B1 N1 S0 B1 S0, this triple to T2 S0 B2 N2 at S0 B2 at S0. So this rotation is exactly given this immediately you can write. Of course, here you have to compute the inverse because this maps this T1 N1 B1 maps E1 E2 etc. this, but you have to start inverse because the inverse will map T1 N1 S1 back to E1 E2 E3. and this will map E1, E2, E3 to T2 and to B2. So composition will take T1, N1, B1 to T2 and to B2, all at this fixed vector, fixed point S0, nothing else. Okay. So that rotation is taken. Okay. So this is important. So that is, which means that M, so let me rewrite this, M, this vector M at T1 S0 is equal to T2 S0. Other points we don't know anything. At S0 there are two vectors, namely the vectors T1 S0, N1 S0, B1 S0, and T2 S0, B2 S0, N2 S0, B2 S0. So there we are applying M N1 at S0 is equal to N2 at S0, and finally M at this vector, namely B1 at S0 is equal to B2 at S0. So this rotation M is going to play. So we are going to rotate the curve gamma 1 with that. So let gamma 1 tilde is equal to M composite. No, tilde we used for that. So gamma 1 bar is equal to M composite gamma 1 tilde. At every point this and S. So we started with gamma 1 and gamma 2. First we translated to get a gamma 1 tilde, gamma 2 tilde. Now we rotate gamma 1 tilde by M. Okay? So now we prove. So this is, so we have brought both of them together at the origin. Now we are rotating gamma 1 tilde. And now we say that after rotating gamma 1 tilde bar, we got gamma 1 bar. So we have now two curves. What is that? Gamma 1 bar and gamma 2 tilde. And that's how the notation came out to be. We prove that these two are same. That means gamma 1 tilde is, this is going to be, so once we prove this, I don't write it, don't get confused. If you prove gamma 1 bar is equal to gamma 2 tilde, that means you can get gamma 1 bar from gamma 1 tilde, gamma 2 bar, gamma 2 tilde from gamma 1 tilde by just applying a rotation. And then translation will give you gamma 1 and gamma 2. So this is the final thing that we will do. But right now let's R identity. This is the claim R C. That requires what? Okay. So for that, okay. So this is a very interesting thing. So before that, let us write down those, these. Because we have changed some notations. Certainly, the earlier ones there was no issue. N1, N2 there is no issue. We are only translating. So N2 is okay. But here we are rotating the tangent normal, binormal of gamma 2 tilde. So let us write down that. So let into T2 bar, then B N2 bar and comma B2 bar. Let's write that convention. B the tangent normal binormal triple Even that could be TNB triple, something we could have written. Anyway, I have not written anything. But triple associated with the new one. What is that? Associated with, oh, this is, sorry, it is not T2, it is S2. Associated with gamma 1 bar. Gamma 1 bar is M composite gamma 1 tilde. Gamma 1 tilde is a translate of gamma 1. So we started with gamma 1, gamma 2, translated. Now one of them we have rotated. We are ensuring that at that point, at one point A. So let us just apply this then. You know that M is a rotation. So it doesn't change tangent, normal, binormal. Okay? So let's find out. That means T1 bar is equal to, T1 bar is the tangent of this. But M doesn't change the tangent change. So it is the tangent of gamma 1 tilde itself, which is already the tangent of gamma 1. So this is equal to T1 at all the points, by the way. And N1 bar S is equal to Ns and N1S, and B1 bar S is equal to B1S as I mean, I did not write, it's M composite, so it doesn't make any rotation, as, oh no, sorry, M composite, sorry, M of this, sorry for the confusion, M of that, okay, it will change, but it will be same linear map. So same linear map changes. B1 as M is a rotation. So it's not an arbitrary linear map, it's a rotation. So it rotates the tangent, normal, binormal at those points. So the linear map actually preserves. When you take any derivative, linear map preserves. But what is important is binormal, when it comes, it's a cross product. So you will get, you actually, I mean, if you remember the computation, then it will be, this is B1 bar is equal to M, what we get is, it's the cross product of tangent and normal. So M T1 cross M N1. But then M is a rotation, therefore this is the same as M of the T1 cross B1, N1. That means M cross B1. This is the only thing that you need to. The others are not. Because they are just second derivative, etc. They are preserved, no issue. And finally, the way we have chosen this is this T1 bar at which I have already written. Yes. So this we should write. So what is T1 bar at S0? T1 bar at S0 is M T1 at S0. But M T1 at S0 is T2 at S0. Only at S0 we are assuming. T2 at S0. At S0. Similarly, N1 bar at S0 is N2 at S0. And B1 bar at S0 is B2. Okay, so this is important. We'll come back to this. Okay, so what have we done? We started with two curves, gamma 1, gamma 2. First, both of them at S0, you translated to and brought it to the origin where they coincide. Both of them are at S0, both are 0. Now, second part what we did was, you look at the tangent normal binormal of S1 and look at the tangent normal binormal triple of S2. Gamma, we gave a new name, gamma 1 tilde, gamma 2 tilde. What we did is, we rotated gamma 1 so that it coincides with the gamma 1, the tangent normal binormal of gamma 2 tilde. And the point S0, nothing beyond that. At that point, we just rotate it so that this tangent normal binormal will become. So, the whole, they coincide. Now we prove that after doing that, not only at that point, now everywhere the two curves are identical. So that's what we're doing. Geometrically, that's what is happening. So this is a small trick, beautiful calculus trick. Okay. So what we do? So remember these notations so that you can, whenever you want, you can go back and check. So we define a function from alpha beta to r. We defined as a at any point s is equal to, using these two. So what are the two things? T1 bar s dot T2 s dot product, so it's a real number, plus other two. N1 bar s dot N2 s plus B1 bar s dot P2 s. So all these are all T1, T2, N1, N2, B1, B2 are smooth, and dot product of two smooth functions is smooth. So right hand side is smooth. In other words, A is smooth as what you started with. And now we are going to show that this A is a constant. First, of course, to show something is a constant, standard trick is look at the derivative and then, okay. So let us take the derivative d by ds. I will not use d by ds too much because it will be too much of fun. So I will use prime for all the, or dot. It's okay. Dot I can use. So a dot s. So this dot stands for the derivative with respect to s. So a dot s is equal to the derivative on the right side is derivative of this plus derivative of this plus derivative of this. Derivative of the dot product of derivative of this component into this plus this dot derivative of this is standard formula. So this is T1 bar dot s dot into s plus T1 bar s dot T2 dot s plus, I don't have too much of space, so I will come down here and take. It's a little bit of computation. N1 bar dot s dot N2 s plus N1 bar s dot N2 dot s plus the last one B1 bar dot s B2 s plus B1 bar s dot B2 dot s. So I have just written, just differentiated the three factors. That's all. Nothing else I did. This is that's it. Now we use reference formula. Okay, so it's a little longer write up, so we cannot help it. So let me write this. So T1 dot is equal to well, before that I want to make one mention. See, we got gamma 2, gamma 1 tilde and gamma 2 tilde by translation, and therefore their curvature and torsion are same as the curvature and torsion of gamma 1 and gamma 2. Afterwards, gamma 2 tilde we did not do anything, but gamma 1 tilde we applied a rotation and got gamma 1 bar. So the curvature and torsion are unchanged by rotations, and therefore the curvature and torsion of gamma 1 bar is the same as K and S. Okay, so that's very important to because we are going to use that. So this T1 bar also has, gamma 1 bar also has same curvature and torsion. So at every point, the curvature of gamma 1 s is Ks and the torsion of gamma 1 bar s is Ts. So let us apply. So T1 bar, that is equal to Ks N1 bar s dot T2s plus, this is bookkeeping, you have to carefully write and just cancel whatever that you get. That's what we are going to get. We are going to cancel everything and then you get 0. So let us do that. T1 bar s is as it is, and T2, just now I said T2 is nothing but the tangent vector of gamma to tilde, which is just its curvature and the torsion are the same as gamma 2. So this is the same as K. So this is Ks N2s plus, this is a bit lengthy because you need N1 bar. N1 bar is equal to, you have to write, and this is minus Ks N1 bar dot is T1 bar s plus Ts B1 bar s dot N2s plus the next factor, you don't have space there, so better write here, plus, doesn't matter, plus, so what do we get here? This is the next factor, this space. So N1 bar dot s, N1 bar s dot, this one is N2. So that is equal to, curvature is the same, Ks minus Ks T2s plus Ts T2s plus the last two. So last two factors will be, this will be B1 bar dot, that is equal to, again curvature and torsion are same, so therefore this is plus minus Ts N1 bar s dot B2s plus this one is B1 bar dot B1 bar s dot, this is minus Ts N2s. That's all. Now just we have to do the bookkeeping. So let us see Ks. Let us look at this factor N1 bar dot T2. Where is N1 bar dot T2? Let us see where is N1 bar dot T2. This is N1 bar dot T2. So now look at this term. This is N1 bar dot T2s into minus Ks. Here it is Ks. So this and this get cancelled. Okay, let's go to this. This is T1 bar dot N1. Where is T1 bar? T1 bar dot N2. It is here. And here it is Ks, here it is minus Ks. So again this goes. I mean, one has to be careful. If you don't make any error, fine. So this term also goes, this goes. Now let us see B1 bar dot N2. Where is B1 bar dot N2? Here. B1 bar dot N2 with minus Ts as coefficient, here Ts as coefficient. So this also goes, this also goes. Similarly, the last one. Where is the last one? Did I cancel something? Oh no, here. N1 bar B2. That is N1 bar B2 with minus Ts here plus Ts here. So everything is. Therefore, the derivative of A is 0. That means A has to be a constant. So hence, this is, that's what I said, it's a trick. A from alpha beta to R is a constant. Of course, we can immediately find out the constant. It is not difficult because let us write down A S naught. That will completely give you the constant. What is A S naught? Because the way we have rotated at S naught, they all coincide. So that is A S naught is T1 bar S naught T2 S naught plus N1 bar S naught N2 S naught plus D1 bar S naught D2 S naught. Just now we have earlier written T1 bar S naught is equal to T2 S naught, N1 bar S naught is equal to N2 S naught, and B1 bar S naught equal to B2 S naught. So these are same as norm of T1 bar S naught square plus norm of N1 bar, whichever way, one of them you can write, it doesn't matter because they are same, at S naught plus D1 bar S naught square. But these are all normal vectors, orthonormality, so this is equal to 1 plus 1 plus 1, and that's equal to 3. Therefore, A is a constant function, and at the point S naught, A takes value 3. That means that everywhere A takes value 3. Therefore, being a constant, AS equal to 3 for S. That's the first observation. Okay? So A is always equal to 3. Now, the beauty is, let us pull back and use that and come back here. So this is going to be 3. AS is this part. This is going to be 3. But let us look at this. What will happen to the modulus of this? So let's write down AS, modulus of AS. That's the probably better way of writing. That's equal to modulus of this. Okay, modulus of T1 bar S, T2 S plus N1 bar S, N2 S plus D1 bar S, T2 S. By triangle inequality, you can easily write this is going to be less than or equal to modulus of this plus modulus of this plus modulus of this. So I don't rewrite, I will just write this. This is less than or equal to this plus this plus this. This is triangle inequality. But what do you know about this? Norm of, this is all dot products. Norm of A dot B is less than or equal to norm A into norm B. So this is less than or equal to norm of T1 bar at S naught S into norm of T2S plus etc. etc. But what do you know about this? This is 1. This is 1. So this whole thing is actually equal to 1 plus 1 plus 1, that's equal to 3. But what do you know about this? This is already 3. So this is identically, modulus of this is also 3. Identically 3. What does it mean? 3 is less than or equal to this number, and this number is less than or equal to 3. Therefore, this number has to be equal to 3. Right? So therefore, now let us look at this is a non-negative real number, this is a non-negative real number, this is a non-negative real number. Okay, so let me write that. Therefore, modulus of T bar S dot T1 bar S dot T2 S plus modulus of N1 bar S dot N2 S plus modulus of D1 bar S dot D2 S is equal to 1, equal to 3. Alright. This is a non-negative real number. And this is going to be less than or equal to 1 because we have already written here the modulus of A dot B is less than or equal to mod A into mod B. So this is less than or equal to 1. This is less than or equal to 1. This is less than or equal to 1. And the sum is 3. You have 3 real numbers. You don't even have to worry about non-negative or anything. We have 3 real numbers. All of them, each of them less than or equal to 3. But their sum is 3. And therefore, all the 3 numbers will have to be 1 each. There is no other option. So, no. T1s dot T1 bar, T1 bar s dot T2s. And I will just write one of them. We have already written here. This is less than or equal to norm of T1s into norm of T1 bar s into T2 norm of T2s. But these are normal vectors, so that's less than or equal to 1. Similarly, this is also less than or equal to 1. This is also less than or equal to 1. So you have 3 real numbers, all 3 of them less than or equal to 1, and then their sum is 3. Therefore, there is only one option, namely, all 3 numbers will have to be equal. So modulus of this is 1, modulus of this is 1, modulus of this is 1. If you look at the function as, we can say a little more than that. What is as? As is equal to T1 bar s dot T1 T2 s plus N1 bar s dot N2 s plus B1 bar s dot B2 s. And we know that this is identically equal to 3 every time. But if you look at these numbers, this number, this is, for any 2 vectors, A dot B is actually equal to norm of A into norm of B into cosine of theta. So it will be less than or equal to norm of A into norm of B. This is a standard Schwarz inequality. So this number is always going to be less than or equal to norm of this into norm of this, but both are 1. Therefore, this number is less than or equal to 1. This number is less than or equal to 1. This number is less than or equal to 1. And you have the sum to be equal to 3. Okay? So, since T1 bar s, this T2 bar s, this is always less than or equal to norm of T1 bar s into norm of T2s and the other 2. I am not keep writing. So this is going to be 1. So this number is less than or equal to 1. Same way this is less than or equal to 1 because these are also normal vectors. This is also less than or equal to 1. But there, that means the sum has to be less than or equal to 3, but it's equal to 3. And therefore, each of them has to be equal to 1. There is no other choice. Not only modulus, the number itself has to be 1. Okay? And so, hence, so this has to be equal to 1. It has to be less than or equal to 1. This is less than or equal to 1. This is less than or equal to 1. But the sum is 3. Therefore, all the 3 of them have to be less than equal to 1. If any one of them is less than 1, then obviously the sum cannot be 3. If the sum has to be 3, then all the 3 have to be 1 each. So hence, when is the inner product of these two? 1. T1 bar s is equal to T2s. What is the inner product? It is modulus of norm of this into norm of this into cosine of the angle between them. Norm of that is 1, norm of this is 1, cosine of the angle between them. Therefore, has to be cosine cos theta has to be 1, which means your theta has to be a multiple of 2 pi. In other words, these two are equal. So therefore, T1 bar s is actually equal to T2 s N1 bar s, etc. But that's not right now. That doesn't affect us. So from this, what have we done? So now your yeah. So N1 bar S is equal to N2 S, and then B1 bar S is equal to S. So from this, immediately you can say your gamma 1 bar S by integrating. You can easily say gamma 2 tilde S plus some constant, because integration. This is T11, T12, T13, this is T21, T22, T33, coordinate wise you integrate. So you get this and this. There will be a constant of integration C1, C2, C3. That gives you, this is a vector. Now what is that vector going to be? That's also easy, because gamma 1 bar at S0 is equal to 0. Go here first. This is anyway gamma 2 shifted, this is 0. This one is, well, I can write it, gamma 1 bar S0 is equal to M gamma 1 tilde S0. Gamma 1 tilde S0 and gamma 2 tilde S0 are 0. So this is M 0, but M is a linear map. Therefore, it is 0. Similarly, because we brought everything together, then we rotated. One of them we rotated and coincided. So obviously that at S0 it is still at 0. That is because we want to apply a linear map. We brought them to origin. If you keep there and rotate, then the whole thing will get rotated. That's why we brought it to origin. And that ensures this is 0. And gamma 2 tilde at S0 is already, this is obtained initially by rotating, by shifting gamma 2 to origin. So that means, hence, this is 0 at S0, this is 0 at S0, therefore C has to be, C is a constant. Somewhere you evaluate the initial condition, 0. So therefore, gamma 1 bar is equal to gamma 2 tilde S. Now, I mean, if you want to get everything done into very neat form, we can write it. What is gamma 1 bar at S? Gamma 1 bar at S is M times gamma 1 tilde at S is equal to gamma 2 tilde at S. This is done. And let us look at this. M of what is gamma 1 tilde at S naught? S is gamma 1 S minus gamma 1 at S naught. That's equal to, what is gamma 2 tilde? Gamma 2 tilde is gamma 2 S minus gamma 2 at S naught. Now you can easily write what will happen. So your gamma 2 is equal to, gamma 2 S is equal to M of gamma 1 S minus gamma 1 S naught minus gamma 2 S naught. So this is, so what do? You start with gamma 1. First go for translation. If you want, I can write that. This is, right here, T. Well, T may be a problem with this, so because I've been using T for tangent. So translation, I don't know what better notation. I don't know. Okay. So you start with gamma 1, translated by this minus gamma 1 S naught. Then rotate by M. Again translate by minus gamma 2 S naught. You get gamma. So from gamma 1, you first apply one translation, then rotate, then again translate. So your gamma 1 was here. You first translated to the origin. Then you rotated. And then again translated back to gamma 2. So you go from gamma 1 to gamma 2 by just using only one rotation but two translations to obtain gamma. So what we say is that if you take two curves, space curves R3, with the same curvature and torsion, then from one you can get the other by using a couple of translations, composite with rotation. So that's the theorem. Up to that, we are unique. So everything else, you give me one, you can get everything, every other curve by using translations and rotations. That's the theorem.